I never get tired of looking at pictures of Saturn. Those rings, they're just awe-inspiring. They're made of ice, rocks, and dust, ranging in size from boulders to small shards, all the way down to micron-sized particles. The other 3 planets in the solar system also have rings, although with a lot less material, so they're harder to see. Here's an image of Jupiter's rings obtained by the Galileo spacecraft at a carefully chosen moment when Jupiter was eclipsing the Sun. That way, we can see the particles in the ring backlit, like when the dust in your house is illuminated by a beam of sunlight coming at you through the window. This one is a false color image of Uranus from the Hubble Space Telescope. It's an infrared image with red, green, and blue assigned to different infrared wavelengths. The rings come through more clearly that way. You can also see a couple of moons outside the rings and some bright clouds on the planet itself. And here is Neptune, as seen by the Voyager 2 spacecraft. It's 2 pictures stitched together, each of which excludes the planet itself, because otherwise the rings would be lost in the glare. Do you see how thin the rings are? They're like strands of silk. Apart from the beauty of these rings, I want to call your attention to a pattern. The radius of the rings varies from planet to planet, from about 40,000 to 250,000 kilometers. But they're all about the same size relative to the planet. The major rings are all in the range from about 2 to 2.5 times the radius of the planet. Why is that? What physical principle sets the radius of the rings? That's question number 1 for this lecture. Questions 2 and 3 are related to the moons of the giant planets. They've all got moons, lots of them. Saturn has at least 60 moons. You can see 3 of them in this image obtained by the Cassini spacecraft, along with a segment of the rings. The big one, way in the background, is Titan, with a diameter of 5,150 kilometers, bigger than our moon. In the foreground is Dione, with a diameter of 1,120 kilometers, and tiny Prometheus, only 90 kilometers across. Here is a family portrait of some of Saturn's moons with their sizes to scale. I want to call your attention to 2 patterns here. First, notice their shapes. Titan looks like a planet. It's big and round, like a globe. The medium-sized moons are round too, but the smallest moons, smaller than about 500 kilometers, are not round. A close-up reveals some pretty weird shapes. Hyperion looks like a potato. Telesto is like a robin's egg. And look at Pan, only 35 kilometers across. It looks like a ravioli. Or is it raviolis? I'm not sure. Anyways, it's not a sphere. So, question 2. Why are the large moons, bigger than about 500 kilometers, spherical, while the smaller ones are potatoes, eggs, and ravioli? Question 3 is about the sizes of their orbits. All of the big spherical moons are far from the planet, well outside the rings, whereas the small moons we find all over the place, including some right in and among the rings. Check out this picture of Daphnis, tucked inside a gap in Saturn's rings. It's close enough for its gravity to produce wavy patterns in the rings. So why are the large moons only found in wide orbits? That's question 3. To answer these questions, we need to expand our discussion of gravitational orbits. So far, we've assumed that the orbiting body is a point mass, an infinitesimally small mathematical point. We've ignored the fact that a planet or a moon is a real object with a non-zero size. Why is that important? Because the force of gravity depends on distance. It gets weaker as you get farther away from the attracting mass. For example, the side of the Earth facing the Sun, the day side, is pulled harder than the night side. These differences in gravitational forces from one part of a body to another are called tidal forces. Tidal, as in ocean tides. Later we'll see the connection between tidal forces and that twice-daily ebb and flow of the Earth's oceans. Right now, we'll consider a more extreme aspect of tidal forces, their ability to destroy a moon. Suppose we have a planet of mass capital M, and let's say it has a moon with a small mass, little m, whirling around in a circular orbit of radius r. Actually, let's start with an even simpler case. Let's just drop the moon starting from rest. What will happen? The moon will accelerate downward and crash into the planet. It doesn't orbit because we didn't give it any angular momentum. Now, let's give the moon a non-zero size. We could make it a sphere, but the math would get too hairy. So in the spirit of keeping things as simple as possible, let's just take one step beyond the point mass approximation. We'll model the moon not as a point mass, but as two rigid spherical rocks, each of mass little m, with their centers separated by some small distance, delta r. When we let go of those rocks, they both fall onto the planet. But will they stay together as they fall? No. The inner rock is closer to the planet, so it feels a stronger gravitational force than the outer one, leading to a larger acceleration and causing the inner rock to pull away from the outer rock. So the moon breaks apart as it falls. In general, the magnitude of the force from the planet is g times big M times little m over r squared. Let's calculate the difference in force, delta F, experienced by the rocks. Since delta r is very small compared to r, delta F is approximately df dr times delta r, which gives delta F equals minus 2gmm over r cubed times delta r. The minus sign means the force weakens with distance. We've learned that the part of the moon closest to the planet is pulled harder by an amount proportional to delta r, the size of the moon, and big M, the mass of the planet. And it's inversely proportional to the cube of the moon's orbital distance. Those are the hallmarks of tidal forces. They grow with the size of the body, the mass of the attractor, and they fall off as the third power of distance. Now, if we want to keep the moon intact, we'll need to supply a force to counteract delta F. We could tie them together with some rope. Or wait a minute, what about the gravitational force between the rocks themselves? They are attracted to each other with a self-gravitational force of g m squared over delta r squared. So if we want them to stay together as they fall, we'd better hope that the magnitude of delta F is smaller than F self. That leads to an inequality in which the g's cancel out along with one of the little m's, and if we rearrange it to put all the moon properties on the same side, we get 2 times big M over r cubed is less than little m over delta r cubed. So if little m is big enough and delta r is small enough, that is, if our rocks are massive and closely packed, we can satisfy this inequality and they'll hold together as they fall. But there's a 1 over r cubed on the left side. As time goes on and r gets smaller, the left side grows rapidly and at some point it overwhelms the right side. Let's call that minimum orbital distance r min. We can solve for r min by setting the two sides equal. Inside of that minimum orbital distance, the moon will break apart. Now, our model of a moon as 2 point masses is not very realistic. You can do a similar calculation, though, for a model in which the moon is a big blob of fluid which can deform and flow in response to the tidal forces. That takes a lot more mathematical horsepower, but the result is very similar. In fact, it's the same as our equation, but with delta r representing the average radius of the moon, and the 1.26 is replaced by 2.44. It's more traditional to write the equation in terms of the densities and sizes of the bodies rather than their masses. We can replace the planet mass, big M, by volume times density, 4/3 pi r cubed times rho. And we can do the same for the moon. With those substitutions and a touch of algebra, the minimum radius comes out to be 2.44 times the planet radius times the cube root of the density ratio. This was first worked out by Edouard Roche, so the minimum distance is known as the Roche limit, the distance within which tidal forces overcome the gravitational binding force of a moon modeled as an idealized fluid body. What if the moon is orbiting, not just falling in? Is there still a Roche limit? Yes, it's the same. And in that case, r min refers to the minimum orbital distance. Suppose a moon made from a bundle of rocks is going in a circular orbit. The rocks that are closer to the star have slightly smaller orbital distances, so by Kepler's third law, they have shorter orbital periods. The outer rocks have longer periods. So, unless the moon's self-gravity is strong enough, the rocks will drift apart over time, the inner ones moving ahead of the outer ones. The moon gets shorn into pieces and strung out into an arc around the star. Eventually, the arc reaches all the way around the planet, making a ring. You see where we're going? This may be where planetary rings come from. Maybe a moon ventured inside the Roche limit, and the tidal forces from the planet sheared it out into a ring. Or maybe two moons collided, smashing into pieces, which ordinarily, given millions of years, would gravitationally reassemble into a moon. But inside the Roche limit, that's impossible. The tidal forces prevent the moon from reforming. And the number 2.44 is a pretty good match to the observed sizes of the rings of the giant planets, which we saw range up to 2 or 2.5 times the radius of the planet. The density ratio is always of order unity because the densities of the moons and the planets are of the same order of magnitude, a few grams per cubic centimeter. So the numbers fit the story. All the planets have a Roche limit, including the Earth. The moon's mean density is around 3 grams per cubic centimeter, typical of rocks. The Earth's is higher. It's about 5.5, because the Earth's stronger gravity compresses its interior and because the Earth has more iron in its core. Given those numbers, the Roche limit comes out to be about 3 Earth radii, whereas the moon is orbiting at a distance of 60 Earth radii, so it's not in any danger of tidal destruction. A good example of what does happen when a body violates the Roche limit came in the summer of 1994, when a comet named Shoemaker-Levy 9 crashed into Jupiter. By the time it hit Jupiter, tidal forces had broken it into fragments, each of which punctured Jupiter's clouds in a different place, making a series of brown spots. Now, at this point in the lesson, you might be a little puzzled. The International Space Station is orbiting only 400 kilometers above the Earth's surface. That's only 1.06 Earth radii, well within the Roche limit. So, should the astronauts be concerned? Maybe you're even getting really worried. I'm standing right here on the Earth's surface at 1 Earth radius. I'm going to get torn apart. But don't panic. We derived the Roche limit by setting the tidal force, which tries to pull the body apart, equal to the attractive gravitational force trying to hold it together. But there are other ways for a body to hold together besides gravity. There are also chemical or material forces that give rocks their rigidity. The silicon atoms in a rock are not held in place by gravity. They're stuck together with chemical bonds, which are ultimately electromagnetic forces at the atomic level. Likewise, my head is not attached to my neck because of its gravitational attraction to my lower body. I can rely on the tensile strength of skin, bones, and muscles. So yes, the Earth is pulling ever so slightly harder on my feet than on my head, and the gravity between my feet and head is too weak to counteract that resulting tidal force, but the chemical bonds are plenty strong. In contrast, Comet Shoemaker-Levy 9 broke apart because it was a loose conglomeration of rocks and chunks of ice with hardly any material strength, so there wasn't much holding those chunks together besides gravity. The lesson is that the Roche limit is only relevant for objects that are held together mainly by gravity. And we can't take that factor of 2.44 too seriously. That's for the ideal case of a frictionless fluid. Material forces allow a body to come closer than that official limit. That brings us to the pattern that I noted earlier, that we can find little moons, smaller than about 500 kilometers, nestled right within the rings, inside the Roche limit. So why is that? It must be because those objects are held together mainly by material forces and not gravity. In fact, you can tell if an astronomical object is gravitationally bound just by looking at it. If gravity is the dominant force, it will be a sphere. It's because each piece is attracted to every other piece. Left to its own devices, gravity draws everything inward toward the center of mass, smoothing out any lumps and making a perfect sphere. In contrast, chemical and material forces are very local. They act only between neighboring molecules or surfaces in direct contact. So, a body held together by those forces can be any shape, an egg, a potato, a person, depending on the history of how those pieces came together. But if we make the object bigger and bigger, gravity becomes more important and eventually dominates over the chemical and material forces. Let's do an order of magnitude calculation to see how big a body has to be for gravity to mold the shape into a sphere. Suppose we have a rock with a characteristic size of r and mass m. Now let's make it slightly larger by adding a single silicon atom. Which is more important, the molecular forces that bind the silicon to the minerals on the surface, or the gravitational attraction of the atom to the entire mass of rock? It'll be easiest to compare the relevant amounts of energy. We learned earlier that the energy levels of electrons in atoms are always on the order of a few electron volts. That's the energy scale of atomic bonds. The energy scale for material forces tends to be an order of magnitude lower because rocks aren't perfect crystals. They're ragged collections of crystals, and the interactions between them are weaker. So let's say the energy released is on average a tenth of an eV per silicon atom. Meanwhile, the gravitational potential energy that's released when we add a mass of little m is of order g times big M times little m over r. For gravity to be more important, we need that to be much larger than a tenth of an electron volt. That gives us a condition on the rock's mass over radius, m over r. And we're wondering about the critical size. So let's write m as volume times density and then solve for r. What we find is that r must exceed the square root of 3 over 4 pi times 0.1 eV over gm rho. Time to insert some numbers. The density of rock is around 3 grams per cubic centimeter, or 3,000 kilograms per cubic meter, and the mass of a silicon atom is about 28 proton masses, or 4.7 times 10 to the minus 26 kilograms. Plugging those numbers in, along with all the constants, leads to a critical radius of about 600 kilometers. Now, we can't take that number 600 too seriously because this was only an order of magnitude estimate. But based on this calculation, we would expect objects much larger than that to be sculpted into spheres by gravity, while much smaller objects can have irregular shapes. And that's just what we observed earlier among the moons of Saturn. So, we've answered our 3 questions. Why are the major rings of the giant planets all within about 2.5 planetary radii? Because that's the approximate location of the Roche limit. Why are the large moons spherical? Because they're big enough for gravity to dominate over material forces. And why do the large moons orbit well outside the rings? Because otherwise tidal forces would break them into smaller pieces. But we're not quite done talking about tides. These concepts that we've been discussing will help us understand much more than rings and moons. Tides are also relevant to planets, stars, black holes, even entire galaxies. For example, in the field of exoplanetary science, rocky planets have been found with incredibly tiny orbits. The current record holder for the teensiest orbit is a planet called KOI 1843.03, whose orbit is less than 0.5% of the size of the Earth's orbit. It takes the planet only 4.2 hours to complete a full revolution around its star. It's right up against the Roche limit. If it were much closer, it wouldn't hold together, and the planet would disintegrate, perhaps making a ring around the star. Stars themselves can get torn apart if they violate the Roche limit. Sometimes a star will be orbiting another star at what seems like a safe distance for billions of years. But then the star expands. It becomes a giant star, as we'll discuss later. This lowers the star's density, which in turn causes the Roche limit to reach out to larger separations. We can see that from the equation. If the rho in the denominator goes down, the minimum distance goes up. A star can also get torn apart if it gets too close to a black hole. We'll have more to say about black holes later. For now, be aware that they really exist, and in particular, many galaxies, including our own, have an enormous black hole sitting at the center. If a star happens to venture too close to the black hole, well, that's the end of the star. In 1988, Martin Rees wrote a paper trying to anticipate what would actually happen. First, the star gets distorted into an elliptical shape by the black hole's tidal forces. And then as the star gets closer, its angular velocity rises rapidly. That's Kepler's second law again. The side of the star facing the black hole has a higher angular velocity than the far side, and the resulting shearing force tears the star apart, creating shock waves and flinging material out into space. The result is a luminous, expanding fireball. Starting around 2010, these tidal disruption events have been detected as bursts of light from the centers of otherwise normal-looking galaxies. The luminosity rises by a factor of 100 in just a few days, and the temperature of this fireball gets as high as 20,000 degrees Kelvin before it fades away over the course of months. Discovering and studying these stellar flameouts is a very hot topic in astrophysics these days. Tidal forces can also act on entire galaxies. Here's one called the Porpoise galaxy. It used to be a normal spiral galaxy, but it got twisted and stretched out into an arc during a close encounter with the more compact white galaxy to the right. Over the next billion years, the porpoise will come apart completely, perhaps making a ring around the other galaxy before they eventually merge together. A more down-to-earth example of tidal forces is the one that I alluded to at the beginning of this lecture, ocean tides. So let's conclude with a few words about the oceans. The Earth's gravity pulls on the Moon, and the Moon's gravity pulls back on the Earth. That means that the Moon exerts tidal forces that, left unopposed, would tear the Earth apart by squeezing it along the direction to the Moon. The Earth's own gravity prevents that from happening, but there's more to it than that. Let's draw little vectors representing the gravitational force of the Moon at different points in the space surrounding the Earth. Close to the Moon, the vectors are longer because the force is stronger. There's also some variation in direction because all the vectors point straight at the center of the Moon. But importantly, the Moon is orbiting the Earth. To see the Earth and the Moon sitting still, like they are in this picture, we must be in a frame of reference that's rotating along with the orbit once a month. That's okay. We are allowed to do physics in a rotating frame of reference, but the price we pay is that we must insert a fictitious force, the centrifugal force. In this case, the centrifugal force on the Earth points away from the Moon with a strength such that at the center of the Earth, the centrifugal force cancels the gravitational force exactly. That's why the Earth is sitting still in this frame of reference. Let's add the centrifugal and gravitational forces and then replot the net force vectors. There's no net force at the center of the Earth. The net force points toward the Moon on the near side and away from the Moon on the far side, where the centrifugal force is larger than the gravitational attraction. And in between, there are sideways forces. Now, imagine the Earth is a frictionless sphere surrounded by a thin layer of water. What would happen to that water? It would feel these net forces and flow around the surface to form two bulges, one on the near side and one on the far side. And then, if that frictionless Earth were to rotate, sliding underneath that layer of water, an observer on the surface would see the ocean rise in height, then fall, rise, and fall again over the course of a full day. That's why we observe 2 high tides and 2 low tides in one day. Now, the Earth is not a frictionless sphere. There's a lot of friction. And there are continents, underwater mountains, all kinds of things that make the picture more complicated. That's why we need tide tables. One of the interesting complications is that the tidal forces from the Sun are also significant. That's why the maximum height of the tide varies with the phase of the Moon. When the Sun and the Moon and the Earth are all along a line, the Sun and the Moon work together and produce unusually high tides. These are called spring tides. When the Sun and the Moon are at right angles, the contrast between high and low tides is reduced, and we call those neap tides. From the relative heights of the spring and the neap tides, you can tell the Sun's tidal forces are not quite as strong as the Moon's. They're only about half as strong. Let's see if we can interpret that. Tidal forces are proportional to the mass of the attracting body over the cube of the distance. So, the ratio of solar to lunar tidal forces is equal to the Sun's mass divided by the Moon's mass times the cube of the distance to the Moon over the distance to the Sun. Now, we could just plug in numbers and get an answer, but let's have some fun. Let's pretend we don't already know the masses, nor do we know the orbital distances. It's 1660 again. We're in Isaac Newton's shoes. Can we learn something interesting about the Sun or the Moon by observing the spring and neap tides? Yes, we can, if we also know about total solar eclipses. The stunning thing about total eclipses is that the moon blots out the sun almost exactly, rim to rim, so they have the same angular radius in the sky. Since the angular radius, delta theta, is equal to the true radius divided by the distance, the observation of total eclipses tells us that R sun over D sun is equal to R moon over D moon, or equivalently, the ratio of distances is equal to the ratio of radii. So, in our tidal force equation, we can replace the cube of the distance ratio by the cube of the radius ratio. And now look, we have m over r cubed for the sun divided by m over r cubed for the moon. That's the ratio of the average densities of the sun and the moon. So, the fact that the sun's tidal force is about half of the moon's tells us the sun's average density is half that of the moon. The moon looks like a rock, so its density is about 3 grams per cubic centimeter, from which we could deduce that the sun's average density is around 1.5 grams per cubic centimeter. I hope you agree it's kind of amazing we can figure out the density of the sun, even without knowing anything about what the sun is, based on some pleasant observations of ocean tides and total eclipses, along with the power of physical reasoning.